So a local minimizer. Okay. So it says, so roughly speaking, it says, so if, so if f again is a function from R to R, okay, and so we have x star is a local minimizer of f. Then, so this is statement number A, and then statement number B is, so for any feasible direction D, okay, gradient of f evaluated at x star inner product with D is greater than or equal to 0. So this translates to English that when we view from the local minimizer, every direction, every possible direction is the direction of increasing, because we are already at the lowest point locally. All right. So today I will learn second order necessary condition. That is, so we learned last time, not last time, but last time I said, okay, so this is greater than or equal to 0. Okay, so this greater than or equal to 0 was the best result we can prove based on first order expansion. Okay, now what happens is today we'll learn second order, which you guys may have already seen in the homework. So that's why I kind of put homework due date next Thursday, because we'll learn this today. Second order necessary condition. Okay. So we said, okay, when we use a first order expansion, Taylor expansion, this is the best we can prove. So we have two cases. That is, this guy is strictly positive. The other is, okay, what if we have a critical point? So here's a second order necessary condition. This is the theorem we will have. Okay. Theorem we will have is, again, x star is a local minimizer of f. Okay. And we restricted ourselves in the case that the gradient is 0. Okay. So because we talked last time, when this is strictly positive, okay, then every feasible direction is strictly positive. This actually implies this guy, you know. So every strictly is positive. It means when we view from the local minimizer, every possible direction is the direction of increasing. But when this is 0, we may encounter a saddle point. Okay, so if we want to avoid that, we want to introduce the second order necessary condition. So we further assume and gradient at this point is 0. So which means this is a critical point. Okay. Now, then, what happens is, okay, so our second order necessary condition is then, okay, then for any feasible direction D, transpose the Hessian matrix at this critical point times D is greater than or equal to 0. So if D can be every possible direction include every unit vector, like if our D can be any vector that has length 1, then this is essentially saying the Hessian matrix is non-negative. Okay. So now let's prove it. The proof is very similar to what we had last time. So D is the direction. This actually means the norm of D is 1. So the norm we talk about for any vector is D inner product with D or D transpose D. So this is the summation of, if D is a vector, has D1, D2, Dn, then the norm of D squared is the square of each of its component. We take sum, then we take square root. So, and now we use the Taylor extension. So for alpha R, so without loss of generality, we can assume alpha in R plus, which means alpha is a positive number. Because otherwise, if alpha is negative, we can just negate the direction of D. So now, we use the Taylor expansion. Okay. Because x star is a critical point, this is 0. Okay. So this implies this guy subtract the function value at the local minimizer is 1/2. So B transpose the Hessian matrix plus C alpha cubed. All right. So we can pull out alpha square, and this is 1/2 B transpose Hessian matrix x star B plus C alpha. The argument is exactly the same with what we did on Tuesday. So we know that this is greater than or equal to 0 because x star is a local minimizer. Okay? This is by definition. Okay? This is a local minimizer. It means a point in its neighborhood has function value greater than or equal to. So this is greater than or equal to 0. So now let's look at this. I mean, alpha squared is greater than or equal to 0, but I mean, it's strictly greater than 0, but it doesn't affect our final proof. Okay. So now what we want to prove is, what we want to prove is this. Okay, this D transpose Hessian matrix D is greater than or equal to 0. So same thing. Now we assume otherwise. So we want to prove this is greater than or equal to 0. So we assume what? We assume okay equals a negative number. Okay? So what happens is, now we can choose alpha. Okay? So how do we reach a contradiction? Is we set this to be negative because alpha is at our disposal. So we choose alpha so that their sum is negative, and then we reach a contradiction. Okay. So we choose alpha equals, okay, we're filling this blank, in a moment. So we choose alpha such that this is 1/2 . So we know that this term is minus beta. So overall, this is alpha squared times minus 1/2 beta plus C alpha. Okay. So here, what I want to do is think about this. Okay. So if C, this constant, is positive, okay? So let's first consider C is negative. So if C is negative, we already reached a contradiction. Okay? If C is negative, alpha is positive, I mean, we don't actually, let's still do this, otherwise argument will get overly complicated. Because right now we haven't used alpha being positive yet. So, okay, so what we want to do is we choose alpha so that this term is still a negative term. Let's say this is negative 1/4 beta. Then overall, this is negative 1/4 beta alpha squared. So this is strictly less than 0. I think the only thing we need to think is alpha is not 0. So now we're filling this blank. So then, this is what? Then we let alpha to be 1/4 beta divided by C. So now we have already reached a contradiction. So this term, so we have reached a contradiction so that because we have chosen an alpha such that this guy equals this whole thing is negative. But this contradicts with x star being a local minimum. So this actually has direct consequences in coding. So by the end of the semester, we'll eventually see it. So if you have played with the LBFGS in PyTorch, which is almost a second order optimizer, so it's limited memory BFGS. BFGS are the initial of four guys, but I forgot the full name. So it actually has a condition checking, okay? Like the second order condition. So this is essentially saying there exists an eigenvalue that is negative. Okay. So there is a switch actually checking, we don't want our eigenvalue or approximated eigenvalue to be negative. Okay. So now we have proved if we reach a contradiction, that means then this implies our assumption here is wrong. So this must implies the Hessian times d transpose Hessian d is positive for any feasible direction d. Again, if d is any direction that has length 1, this is essentially saying the eigenvalue of this guy is greater than or equal to 0, so which we'll do in a moment. So today we'll learn sufficient condition. All right. Second order sufficient condition. So second order sufficient condition is slightly different than the necessary condition because we said, okay, so remember this is like a proof class 101. So this is statement of A, this is statement of B. A implies B. Whoops. Then B is called the necessary condition of A. But for that, we'll do it in reverse. We'll find conditions. So this is a sufficient condition. That means if x star is a critical point, and the Hessian at x star is strictly positive. So this means any B transpose Hessian x star B is positive. Okay. And then x star is a strict local minimizer of f. So this is a theorem. All right. So now this is like in reverse, right? In the necessary condition, we assume, okay, so we know that x star is a local minimizer, and what condition, this x star must satisfy. So now we give a sufficient condition. So this is a very strong condition, these two. If the gradient at f star is 0 and the Hessian matrix at f star is strictly positive, think about our famous function. Think about famous 1D function, that is f of x equals x squared. And in ND, so we have also another function that is x norm squared. And this is a famous L2 regularizer we use all the time in machine learning. Okay. So, to prove this, we need several things. Okay. To prove this, we need several lemmas. Lemma 1. So this lemma is from linear algebra, but if only undergrad linear algebra is required in this class, so we still have to prove this because I don't think undergrad linear algebra covers something like this. But we mentioned this in the first week. That is, if A is a symmetric matrix with real values, okay, all of its eigenvalues are real. Okay. All right. I mean, the proof is very simple, but it's literally using the definition of eigenvalues and complex vectors. So if we have a complex vector, so for example, if we have a complex vector, so this is like the set of real number. Complex number is C. Okay, so if we have a complex vector, okay, so x equals something like A1 plus B1I to AN plus BNI. So by the way, if you have played PyTorch, there are lots of neural network feature complex weights. For example, those Fourier neural networks, so which I'm currently working on. It features all complex weights that makes optimization kind of bad, but kind of good in the sense. Okay, so first we define, this is called the complex conjugate, okay, or simply conjugate. So the complex conjugate of this is, we simply take the complex conjugate of every entry. So, and we define the length of this x squared is x dot product with its complex conjugate, okay? Or its complex conjugate dot product with itself, or we write it as complex conjugate transpose x. Actually, we have another name for taking the complex conjugate and then transpose it as a name. That is, this is Hermitian. Okay. So it can be denoted as either x super h or x star. But I don't want to use this notation. So this notation is used in many optimization textbook. But let's stick with this. So this is called the Hermitian conjugate of x, which equals X complex conjugate take transpose. Okay. Yeah, over X. Yeah, this is, and X H equals.
I'd also say that, like with, in some math text and some quantum computing text, is XORed.
Oh yeah, you can use that. Yeah.
Yeah.
We call it dagger.
Dagger. Yeah, that's what I knew.
Okay. Yeah, like this gentleman suggests. Okay, so sometimes it's denoted as this as well, so it's a dagger. So if we played with LaTeX, this notation can be typed as \dagger. Dagger is literally the dagger.
Yeah.
So yeah, but let's use this. Okay. So the proof is pretty simple. We assume, okay, X is an eigenvector of A corresponding to an eigenvalue lambda. Okay. So right now, what we know is this guy is real, but we assume X is a complex vector and lambda is a complex eigenvalue. So what we want to show is the complex conjugate of lambda is lambda itself. Then this proves lambda is real number. Okay, so because if someone's complex conjugate is this number itself, it just means its imaginary part is here. Okay, so let's take the complex conjugate on this first. Okay. So if we take the complex conjugate, it's equivalent to taking the complex conjugate on each term. But this is real. A is real, so we have something like this. Now what we want to do is we multiply. So this, let's say, this is equation number 1. Then we multiply the Hermitian of X on the left side of 1. This implies X Hermitian A X equals X Hermitian lambda X. But lambda is a scalar, it's a complex scalar. So this means we can, okay? So we can switch the position of the Hermitian and lambda. What happens is, what we have is, keep this in mind, X Hermitian times X is a scalar, so this becomes a scalar. And this scalar is a real scalar because this is X squared, so this is a real number. Okay, so this is real. And what we can do is we divide this to the left. So we have this is so we have this. I mean, this is called the Rayleigh quotient. I mean, in the context, so some of you guys may already seen this. In the real context, this is nothing but X transpose AX divided by X transpose X. So it's called the Rayleigh quotient. And let's write down. Furthermore, let's think about this. Okay. Now the argument is pretty straightforward. in that if we take the complex conjugate of x, of lambda, sorry, it equals the complex conjugate of this, and of this. All right. Now we look at this formula. Okay. So what happens is this tells us, if x is an eigenvalue corresponding to lambda, this formula tells us the complex conjugate of x is still an eigenvector, but corresponding to the complex conjugate of its original eigenvalue. So this tells us this is an eigenvalue. If this is an eigenvalue, then this is an eigenvalue as well. Good?
Can you explain it again?
This is the definition of eigenvalue and eigenvector, right?
Yeah.
This is also the definition of eigenvalue and eigenvector,
Oh.
right? A times a vector equals a scalar times a vector. So now it tells us this vector is the eigenvector corresponding to this eigenvalue. So if x is, the eigenvector corresponding to this eigenvalue, then x complex conjugate is an eigenvector corresponding to the complex conjugate of original lambda eigenvalue. Okay. So now the argument is kind of straightforward now. Okay. A is real. Okay. So what's happening is this is true. Okay? It's because x bar is still an eigenvalue of A. But this is also, by definition, lambda. Okay. So the major key to use in this proof is A is real, and if A is real, then the complex conjugate of the eigenvector is still another eigenvector, but this proves the Rayleigh quotient will be the same. So this is lemma 1. We need another lemma, unfortunately. But all of these are useful. For example, when you're trying to debug your customized optimizer code, you extract the Hessian from the auto differentiation of PyTorch. You check the eigenspectrum, you find, oh, it has complex eigenvalue. Oh, then, yeah, something is wrong. So you extract the Hessian from a parameter group of the neural network. You check, for example, your dot W dot, like Hessian, and you find, and you check the spectrum of it, and you want to prove the convergence, but then you find, oh, we have complex eigenvalues. Then not bad. Okay, so lemma 2. So A is a real symmetric matrix. Same setting. Think about Hessian of some real function that maps Rn to R. Okay. Then A being greater than or equal to 0, greater than 0, but we can change it to greater than or equal to 0, this still applies. This means for any D in Rn, so D is not 0, or we can restrict D's length to be 1, okay? D transpose AD is strictly greater than 0. Okay, so this A is positive definite, I'll say. So A is symmetric positive definite. This is equivalent of saying the minimum eigenvalue of A is positive, or lambda mean of A is positive. Okay. So this we require, so to prove this, I mean, this is also very useful as well. In advanced linear algebra class, I mean, this may be one of the few theorems that's taught in the first place. Okay, so let's prove it. So what we want to show is, eventually, okay, so we'll get something like this. So from here, eventually we'll get something like this. So first, so A has a diagonalization. That is, A equals U transpose lambda U. Okay. So where lambda is all of its eigenvalues, lambda 1, lambda 2, lambda n, and it may have multiplicity, okay? So let's say this matrix is n by n, and U is a unitary matrix. What does it mean by unitary matrix? Is its inverse is its transpose. Okay. If it doesn't have a diagonalization, the proof will be much more complicated. So let's focus on this case. And then it's kind of straightforward. Then E transpose AD is E transpose U transpose lambda U D. Okay? Now we use E transpose U transpose is UD transpose UD. Okay. So this is Y transpose lambda Y. Okay. Where Y equals U transpose D. So U is a unitary matrix. And unitary matrix is an invertible matrix. An invertible matrix. Okay, so linear algebra 101. For an invertible matrix, it maps Rn to full Rn. Okay. So U unitary implies U is invertible because its inverse is itself by definition. Okay. So if it's an invertible matrix, the linear transformation, that is U D, okay, it still maps every possible direction D to every possible direction like UD. So the map D maps UD is surjective. And moreover, the unitary matrix has this special property, that is, the norm of a unit matrix times a vector is still this vector's norm. Okay. So this is a property of the unitary matrix. So this is still 1, so which means our y still represents a direction. Okay. Now let's continue in this in this expression. So this is y transpose lambda y. This is y1, yn, okay, and this is lambda 1, lambda n. This is a diagonal matrix. y1, y2 to yn. If we compute this matrix vector product, this is an n by n matrix, this is an n by 1 vector, this is a 1 by n vector. So for example, if we compute this, we'll get, so because this is a diagonal matrix, compute this matrix vector multiplication is super straightforward. Okay. So first row is lambda 1, y1. Second row, lambda 2, y2, and blah, 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 lambda n, yn. So this is nothing but, now, y1 times lambda 1, y1, y2 times lambda 2, y2. So this is the summation from I from 1 to n, lambda I, yi squared. Every term is non-negative. So what happens is, this is greater than, so because every term is non-negative, we can safely say, because every lambda I is greater than or equal to the minimum eigenvalue. Right? I mean, it's a minimum. So no eigenvalue is less than that. So it's greater than or equal to lambda minimum of A times yi of 2. Okay. Now, because this factor of lambda minimum is in every term, we can pull it out. Okay, we can pull it out. This is yi squared. Summing it up. But y is a direction as well. This is 1. So this is lambda minimum of A. Okay? So we have shown that where we start? We start from here. This guy is positive. And we ended up with lambda minimum of A. So this is must be positive. positive as well. If we assume that is positive. Okay. So this implies, okay? So this implies if if lambda minimum of A is positive, then DAD must be positive for any direction. Actually, the converse is true as well, because we derive from here, 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 and we'll see that if that is positive for anything, we can actually choose a specific eigenvalue that corresponding to lambda minimum, and then lambda minimum becomes positive as well. So, but I'll skip that. The other direction is kind of simple. So let's prove this.
The line below this.
Oh, here?
No, the other side, sorry. D maps UD.
Oh, here?
Yeah.
Okay. So, so in linear algebra, there is a theorem says the following. So if A is invertible, A is invertible means let's use X. Yeah, let's use X. Let's use X. It means for any B in Rn, this has a solution. X equals A inverse B, right? This is linear algebra. Okay. So if we can actually change this too, okay? So if we define a map, a linear transformation from X to AX, AX can achieve every possible B in Rn. This is another saying of this AX equals B has a solution, which is a linear system. This is a square linear system. So A is a square matrix times then Rn vector equals Rn. So this is a special regime that our number of equations, which represents the physical constraints, equals our numbers of degrees of freedom in whatever system you may think, like common filtering, signal processing, elasticity, mechanics. So the number of variables corresponds to number of degrees of freedom, and this is a number of constraints. Once they are equal, we have a very special regime in that this has a solution for every possible right-hand side. It just means this map is surjective. Okay. So there is only a tiny caveat is because that is only invertible. This is unitary preserved distance. So we consider the set that is a subset S that has all the directions, contains all the directions. That is all the possible vectors are n that has distance 1, okay? So if we have a unitary matrix, because unitary matrix preserves the length, this is subjective on this set S. So now let's prove this. I mean, once we have proved these lemma, proving this is actually pretty straightforward. It is to plug in the Taylor expansion of X star So by lemma 2, actually by the proof of the lemma 2. Okay. So this, because the Hessian matrix, okay, the Hessian matrix is symmetric. The reason is because we're taking partial derivative with respect to xj first, then taking partial derivative with respect to xi, so is the same as we're taking partial derivative with respect to xi first, and then xj, because this is the ji entry of our Hessian, and this is our ijth entry of the Hessian. Okay. So this one is symmetric. And this means, by lemma 2, this is greater than so this is greater than over the lambda minimum of this Hessian matrix times B transpose B, and this is B square, okay, which is what? For lambda minimum is the minimum eigenvalue of the Hessian matrix at x star. And we had an assumption that this is positive. Anyway, so now let's simplify this expression again. We'll find this is this guy, okay. So now, by our assumption, by the ifs, we assume this is 0. This is greater than 0. if we assume the matrix is positive definite. So now what we have only left to show is we can choose alpha small enough so we can choose a bound such that, for example, we can set like a borderline bound. So we let this to be 0. Okay. All right. So then this implies alpha is what? So alpha is minus 1/2 lambda minimum divided by c, right? But this is a borderline. So this is in our scratch paper, okay? So this is in our scratch paper. What happens is if we choose, so now we choose an epsilon equals absolute value of that. So equals absolute value of that, which is 1/2 lambda minimum divided by 1/2 lambda minimum divided by c. If we choose epsilon equal this, then we can say, for any alpha that has absolute value less than epsilon and greater than 0, so the term which equals alpha gradient of f at this critical point d plus 1/2 alpha squared d transpose Hessian of this d plus c alpha cube, is positive. Okay. So we solve the borderline alpha, so on our scratch paper, and then we can safely assume that when alpha is less than this borderline, so this term may never surpass the positivity of this term. Okay, so that's the intuition. So once we set that this is greater than 0, and we have proved that, then what we have proved is if we set these two conditions to be true, then this guy is always greater than, strictly greater than this guy, and that actually proves. So this proves x star is a strict local minimizer. All right. So this actually, so this is already done, but I want to talk about this local. So in machine learning, the localness is very important. Why I'm saying it's important because global minimizer is normally non-existent for minimization problem in machine learning. So every local minimizer will be a good minimizer. So the localness, why I'm talking about localness is because alpha, so as we can see here, alpha depends on the Hessian matrix at the critical point, which in turn depend on the point, okay, which in turn depends on, so where this point is, okay, so where this point is, it means It's different point by point. So, I mean, from the proof, because we see that the more positive this is, actually the better minimum will be around that point. So this is a very qualitative assessment of, like our local minimizer. So the lambda minimum of this matrix is more away from 0, so lambda minimum. Then we can see that this term has less chance to surpass this term, okay? So actually the analysis, if one of the famous paper, study the 2016, this neural network model for the ResNet. So this is a famous paper in 2017 study, the loss landscape of ResNet. So one famous assessment is the loss landscape becomes much better because the Hessian becomes much more positive around local minimum. And I mean, there's other paper like study the Hessian of neural network based loss function. For example, there's another paper called lottery ticket hypothesis. So it's a very famous paper. It won the best paper award in 2019. I cleared. But I mean, if you guys are interested, you can check on it. So, but now let's move to the next. So gradient descent.
So we would eventually use alpha to bound our learning rate, because if alpha is too big, we could step out of our well and step someplace else.
Yes, exactly.
Okay.
So this is like the mathematical reason why we can't choose too big alpha, because the positivity around our local minimizer is local. Okay. So again, this is our problem. Yeah, why I'm using blue. So this time we consider the non-constrained problem. X is in Rn, f of x. Okay. And we've learned the negative gradient of x in the direction. So this one is where the function aligns with the direction where this function decreases fastest at this point x. The gradient descent algorithm is actually quite simple. It's quite simple. So we'll illustrate using a quadratic function again. So it's full iteration number 0, 1, 2, ... Okay. Such that the next iterate, so we call this the next iterate, okay, this is like our next position we want to be in, equals the previous iterate. So this is where we're currently at. Subtract alpha sub k times the gradient of f evaluated at xk. Okay. Xk. So this is called the step size, or in common machine learning context, this is called the learning rate. All right.
Step size.
Yeah, we'll use step size. This is our textbook uses. All right. So this is a famous gradient descent algorithm. Is we start from a point and we follow the direction of the negative gradient. So there are several aspects of this, and we'll analyze using a sample problem, for this problem. So there are several problems to consider. The first one is what does convergence mean? The convergence is asked the following question, that is when to stop, or our stopping criteria. Okay, because this algorithm is like can go indefinitely. Okay. So why it can go indefinitely? Because even there exists a local minimum, once we get closer and closer to the local minimum, this term will get closer and closer to zero. So we'll never reach that. So but we're getting closer and closer. So it's a limiting process. But so there are several conditions. One of let me use capital K. Let me still use K. One of the famous conditions is this. So we choose a small epsilon. Okay. Once we choose a small epsilon, once our gradient magnitude is less than this epsilon, we stop. Okay. So this actually has a huge drawback. Like huge drawback, because we may getting near to a saddle point that this is zero, and then we stop. We're at a saddle point, which is very bad. Okay.
Can you repeat that again? The saddle point, what?
Saddle point is.
Yeah, I know the saddle point, but what you said.
So normally, for example, so if we are getting closer and closer to, so what I'm saying is, but this involves, for example, the typical loss function in neural network in machine learning involving something like a neural network, which is nonlinear, non-convex. That is, we can prove, actually show, saddle point. If we reach the saddle point, it's actually not a good, for example, a regression result for what we want. Okay. So intuitively, we have to avoid saddle points. There are other criteria. So the other criterion is our algorithm won't move anymore. That is, okay. I mean, the bottom is just to make sure this is not zero. Okay. So this condition is very common as well. It's like saying we choose a small epsilon so that our gradient descent algorithm doesn't move that much. Okay, so it's like our next, for example, we pull out all the state dictionary from a neural network. Okay, we subtract them, we take the norm, we find, oh, it's less than 10 to the negative 8. So we're doing useless job, you know, in that
Right,
optimization.
so in that, I mean, in that case there, you're looking at the percentage change over time until xk gets so small that then you're just looking at the absolute change. I mean, that's what that max, divided by the max is.
Yeah, this
You're going
is
from-
relative change.
Yeah, you're going
So
from-
this is just to avoid, you know, dividing by
Yeah,
0.
yeah, you're going from a relative change to an absolute change when you get small enough. Okay.
Yes. Okay, so the best one among all three is actually the gradient doesn't change much. Okay. So this is a relative change in the gradient is small. Okay, not gradient itself is small. And so the next issue is, so we'll learn these issues in the next class for a simple problem. So next issue is step size. Okay. Which is alpha k. How to choose alpha k. So we'll learn next time. Okay, how to choose alpha k for this simple problem. That is f of x is 1/2 x transpose qx, and q is SPD matrix. Okay. So how to choose alpha k for this specific problem? So we'll see that it's actually 2 over the sum of the minimum eigenvalue plus the biggest eigenvalue of q. Okay. So, but anyway, so let's continue next time. So next time we'll show convergence and step size for this simple problem.